Okay, so what is an acid? There are a couple different definitions of an acid. The one that we use most commonly is the Bronsted-Lowry acid-base theory. Any H plus is called a proton, and an H plus donor is an acid. And an H plus acceptor is a base. Because you have a donor and acceptor, these two go in pairs called conjugates. So let's look at a common reaction. We're going to put acetic acid, which is vinegar, a carboxylic acid, into water. And of course, it's called an acid because it's an acid. So it's going to lose its proton to the water. So the water is acting as the base. And when the proton here goes over to the acid, you get H3O+, which is called hydronium ion. That's called the conjugate acid. Hydronium is the conjugate acid of water. And then you make acetate, which is the conjugate base of acetic acid. Now, from your general chemistry class, you would remember that you define the Ka of any acid by the equilibrium expression where you put H3O+, the products over the reactants, H3O+ times the concentration of acetate all over the concentration of acetic acid. You don't include water because it's a liquid and its concentration does not change. Now this value is 1.74 times 10 to the negative fifth. The smaller the Ka number, the weaker the acid, because we don't have much of the products here, so the reactants are favored. Whoa, that was an ugly line, but that means that a weak acid has more of the reactants. The weaker the acid, the more the reactants. Now, in organic chemistry, we don't tend to use these numbers very much. We use what's called the pKa, which is just like the pH, it's the negative log of the Ka. And that, for this value, would be 4.75. Now, a couple things. pKa is not the same as pH. pKa measures the acidity of the molecule. In other words, how much the molecule wants to donate a proton. pH, on the other hand, is equal to the negative log of the concentration of the H+. And that measures really the amount of H+ in solution. So it is a measure of the acidity of a solution. So I have listed down here the pKa chart of the acids that are used in organic chemistry. At the top is HCl, which is a strong acid. It completely dissociates. Now, its pKa is -7. Well, that doesn't happen in water. The first two, these numbers are measured in a solution other than water. So strong acids have very low pKas. So the arrow going here shows the strength of the acid. Now, if you have a strong acid, that means its base is weak. In fact, in my class, I call Cl- not a base. It's worthless. It has no ability in water to pick up a proton. And so this arrow shows the base strength as it goes down. So NH2- is the strongest base that we use in organic chemistry. Now we can use pKas and this chart to figure out whether a reaction will go forward or backwards. So if I take acetic acid, again, vinegar, and I treat it with a base, the conjugate base of ethanol, which is called ethoxide. Oh, I wrote it backwards, but either way. And I'm going to just have that proton hop on over, and make acetate plus ethanol. Even if you don't understand what's going on, let's look at the pKas. In other words, you can't recognize what's going on. The pKa of ethanol is 16. The pKa of acetic acid is 4.7. And so now we look, this is a stronger acid than ethanol. So what acetic acid is a stronger acid, which means ethoxide is a stronger base. Well, stronger things do what they're supposed to do. They react. So this reaction will favor this direction. Another ugly arrow. Because this reaction has the products favored over the reactants, this reaction has a K value greater than 1. So in other words, this reaction will go this direction, forward. So if you look over at this chart, acetic acid will be able to donate a proton to ethoxide, the conjugate base of ethanol. Well, let's try and go the other way. Let's take phenol, which is a benzene ring, like this, with an OH attached to it, and let's react it with acetate. And do the same process again. So take the proton that's acidic and pop it on over. So we're going to make acetic acid as the conjugate acid of acetate, plus phenoxide, the conjugate base of phenol. Write the pKas under the acids. These are all defined by the acids. So it's 9.9 and 4.7. Because this is the stronger side, stronger acid, stronger base, the reaction will go backwards. It will not go forwards as written. So the K value for this reaction is less than 1. And if you look, phenol will not be able to donate a proton to acetate.